So we're going to start discussing compressible fluid mechanics, what it is, where it appears in engineering and the natural environment, some of the challenges, some of the practical applications, before we then proceed into discussing some underlying theory. So the first thing is compressible. What do we mean by compressible? Well, we have an intuitive sense of what compressible means. If you compress something, it means you can squash it. And this whole notion that if I have a volume of fluid with an initial density rho naught, I apply some force to it, however that may appear, then this will change to a density which is quite different from before. T. The point about being compressible is that rho of T is not equal to rho of naught. Now, the partial description is interesting because it gives this notion that it's a small little pocket, and that pocket in fact moves with the fluid. As we've discussed in our review of fundamental concepts of fluid mechanics, this gives this notion that it's what we call a Lagrangian analysis of a parcel of fluid parcel. So something that moves with the fluid, the density changes, we're kind of saying that d rho dt is not equal to 0. And in fact, if that parcel is moving with the fluid, rather than using the capital D's, we have a special symbol for it, which is Lagrangian derivative with respect to time. And this has a very specific meaning because it means that it's got this notion that the can vary very spatially. This occurs from the spatial variation quantity, and this is the temporal. So what this is saying is that the density of a fluid particle changes with time. Now, it doesn't mean that the density is constant everywhere. It doesn't mean that it's constant and uniform. And so we have in many practical cases in the ocean, for instance, where the density of the fluid has for instance, a spatial variation with height. Typically, it decreases with height to make sure it's stable, stratified flow in the ocean, but that's not an example of a compressible fluid. So there are problems where d rho dt itself is not 0, as we see stratification, or where the grad rho is not 0. These are not necessarily compressible flows. Now, how do we change the density of something? Well, if we're going to squash something, as we imagine, we're going to apply a force to it. That force might be applied rapidly over a short period of time. For instance, if we're accelerating air to create sound, so fast acceleration over a short period, we take an object, a ball or a tuning fork, we vibrate those ends very rapidly, then that will create a sufficient perturbation in air to generate sound waves that can propagate. And so that's going to be the unusual element to this problem, that acoustic waves propagate through medium. If you have a weak body force but applied over a very large distance, and so one example of that is gravity. If you apply gravity over the atmosphere, let's say over 10 kilometers, then you'll find that the density will tend to vary exponentially with height, rho z, with an e-folding distance of about 7 kilometers. And so our understanding of the atmosphere can't be modelled we can't neglect compressible effects when we're looking at atmospheric processes. The flow in this case tends to be stratified and support waves. Now these are the third case is the case when the flow is moving so fast that the pressure variation due to the inertia of the fluid is so strong that it causes the gas to be compressed. So this is really, if we can say, this is more the engineering problem, and it's the one that's going to be the focus of our course. So sound is generated in an in a lot of different cases. And what's pretty interesting, I mean, there's a lot of environmental work at the moment to do with sound generation from wind turbines and from the exhaust of gas turbines. And so sound in the planetary boundary layer has some interesting properties, very much affected by shear. Sound here, we generate a lot of noise. Then sound waves, as you would tend to think, move in a straight line, but they're significantly, the wavefront is significantly affected by shear, and so sound waves have a tendency to turn in shear flows, and so you can end up with quiet regions upstream of noises, in order that because of the consequence of shear in the planetary layer, and so you end up with these kind of quiet regions upstream. So sound generation is important in atmospheric flow problems, particularly the environmental side, and also in the ocean. So there's a big push towards reducing sound generation from machinery and also cavitation from propellers that the IMO is pushing forward. The detection element is quite fascinating from a kind of an evolutionary side, and studying how the ear works allows us to develop some our understanding of acoustic impedance in some particular problems. So the ear is quite a magnificent evolutionary detection device, and it's got a number of features to magnify acoustic signatures in the air, which are very, very weak, in order for them to be detected. So there's three things. This, first of all, is the ear canal is basically like a close-end pipe, and so there's the potential for generating acoustic resonance with wavelengths that are which are 4 times the length of the inner ear, which is outer ear, which is the ear canal, which is about 1 centimetre. End up with a standing wave. X. Now the acoustic signature is amplified by the cylindrical cavity, which then forces the eardrum to move backwards and forwards. The acoustic impedance between the air and the liquid is so high. There's a mechanical system to overcome that impedance, because this is essentially water. This is air. And if you're underwater and someone shouts to you above it, you won't hear anything, because this acoustic impedance, mainly driven by the fact that the density difference between the water and the air is so large. There is a speed of sound difference, but that's probably only a factor of 3. And then there's an amplification through the cochlea, which has again it's got a window, and then it's got a membrane with a tapered cavity, and this generates an acoustic streaming on the surface of on this membrane, which causes hairs to be jostled around, and which are converted to electrical signals. So Lighthill, who was former provost at UCL, put together the basic theory of this. Now, Lighthill's paper is interesting because there's no equations in it, and I think it's probably, I remember when I read it, I think it's probably 30 pages or maybe 40 pages long, but I think there may be 1 or 2 equations in it. So it's a real physical explanation of those complex processes that occur in the inner ear. Transport, so these are really kind of antique photos of what's happened in the past. These obviously are not running at the moment. Concorde, whose origin from the late 50s, early 60s until it was built in the late 70s, was an incredible craft. As you see, running at supersonic, Mach number 1.8, we'll discuss what Mach number is later, but it's got some quite amazing design features, designed in a time when electrical computing was at its infancy, so mainly through basic calculations and wind model testing. The wind models are actually in the Science Museum, very small. We'll talk about dynamical similarity later. But the interesting thing is it's got a delta wing, flared delta wing, a adjustable cone, so we'll see a big feature of supersonic craft are variable geometry, and we've got these gas turbine engines with a variable inlet geometry to ensure that the inlet flow is shock-free. This was obviously, well, the real challenge of using domestic supersonic craft is that they generate a sonic boom over land, which is why in the end they're only used between Europe and New York, or east coast of the US. This is Blackbird. This is running at Mach number 3.4, far above, I think probably running at 10K, a height of 10K. At the time it was built, the US didn't have enough titanium, and so in order to get the resources together to build it, there was a lot of smuggling and espionage in order to get the titanium ore from Russia via Africa back to the US. What you'll see here is that it's got, again, a flared cross-section, sharp edges, and you'll see this cone at the inlet. There's an afterburner here, and what we'll discuss later on is why the geometry is with that particular shape and why that shape changes as the Mach number increases. The challenge of running a craft at subsonic and supersonic, because obviously it has to start off at subsonic speed, is that what is designed to run efficiently at high Mach number is a disastrous design feature at subsonic flows. So you need to be clever with your design, and that's what they overcame. This was one of the space shuttles. I'm probably a bit optimistic about how low the Mach number is here. It's probably 20 to 25. It was initially going through the upper atmosphere. And so what's interesting about this design was that it had high lift, so L over D is probably about 1. It's initially at 1, and then as it's going through, and it quickly becomes subsonic. At the later part, that goes up to 10. Not quite a flying brick, but the Mach number starts off at 20 to 25. It's high because if you're coming in, you look at the Earth's escape velocity, it's about 11k a second. And that quickly has to decrease down to something a bit more meaningful, like, at sea level, speed of sound is going to be about 340 meters a second, so that has to decrease down to 340 meters a second, and then ultimately down to 0 in order to stop. And so there are some very interesting features of this shape. Particularly the fact that there's a lot of heat dissipation due to the presence of these quite severe bow shock on the front. Now that's a feature in all of these, that the dissipation that occurs on the surface, on the attached boundary layers, cause a significant amount of heating. So compressible fluid mechanics, on the practical side, is both a fluid mechanical problem, a thermodynamic problem, and also one associated with material selection. Big push at the moment is obviously on space engineering. As you can see, what's happened in China with their space station, with a very successful collection of more than 1 ton of moon rock, and with their Mars mission, you can see that there's a kind of a space race going on at the moment. While we think of space engineering as a modern subject, the fact is that the last time someone was on the moon was in 1972, and in total only about 12 people have actually been on the moon. Most of the designs for this, the basic concepts of rocket design, really haven't changed very much in 50 years, and what has changed is really, if you see here, the control system, the electronics, material selection, construction. These would be the main changes that occurred on the space engineering side. Now, as we move forward, you probably kind of realise that Musk has put an awful lot of energy and resources into SpaceX. SpaceX was obviously an ambitious project, big gamble. So if you follow what Musk has done, you'll see that they were very close to bankruptcy at the beginning. Now, what's interesting is that the whole idea behind SpaceX is that in order for space to be accessible to people, the cost has to drop. If for the cost to drop, you have to use your craft. And so the idea is that the rocket engines will be renewed every probably 100, maybe 1,000 trips, and a lot of the components are replaceable. Not the whole thing, but parts of it. There are some interesting design features associated with the pumps. So there's a turbo pump, gas turbine engine driving a turbo pump for both the fuel and the oxidizer. The fuel in this case this one will be methane. And so this leads to a very high mass flux and an enormous thrust. I think the interesting thing about the engine is, I think, the pressure in the combustion chamber. The combustion chamber itself is a thing that actually supports the thrust. That's where it's effectively pushing the whole structure up. Is the highest so far. I think it's probably, I thought it was 6 megapascals. Seems, yeah, it seems a bit low, but. Now, compressible fluid mechanics, obviously we see it really often in the internal combustion engine, where stuff is literally compressed, and we see it also if we look for astronomical applications. If we look at the Sun and we look at the Jehovah planets, or the gas giants, and we'll see that they're mainly a hydrogen, helium, ammonia, methane clouds with liquid helium, liquid hydrogen metallic core. And so in all these cases that we use a compressible flow formulation. So when we want to pump things and we want to exert thrust, we want to compress gases in order to pump them. And if we look at just the notional design of a fridge, I think this is the original. I think this is a steam pump. Forget this, but I think there's a steam injector which entrains ambient gas, and I don't know if it's here to create a vacuum or here to pump, but I think this is probably an old design from 1890s. But gas compression is quite important for pumping and the conveyance in long pipes. It's a fundamental part of engineering, so not only transport, but transport of gases and liquids. So what are we going to cover in this course? Well, we're going to start at the beginning. We're going to start off with what a normal shock is, and then we're going to build up our basic concepts around particular flow structures, which is a normal shock, an oblique shock, and an expansion fan. Expansion fans kind of being the opposite to something that's compressed, a shock. And we're going to try and apply all of that stuff for the first four. These are the basic building blocks. We're going to be able to apply these various situations. So forces on supersonic aerofoils, nozzles and inlets, and diffusers and outlets. So this one, say group A, can be all understood from these first three lectures. And these bits, part B, these bits here are kind of linked together because they have a, well, they're linked because the methodology used to solve them employs a particular reference state, a critical reference state. And in fact, in practical problems, when we're looking at flowing pipes, which are changing diameter, there are also, or changing area, we also need to take into account the possibility of friction and also adding or taking heat away. We're looking at rocket theory, which we'll be covering quite a lot of detail. Then what we need to be doing, we need to be looking at why nozzles are rocket nozzles are the shape they are, which is this component here and also this one. So when we're looking at diffuser and outlets, we'll actually be doing a force analysis to look at thrust, parasitic drag being an important component of that. Now the interesting thing in relation to year one, so year one, as we've discussed, takes into account what we call, or makes use of what we call an integral formulation of fluid mechanics. The notion that we're actually looking at, for instance, forces which can be described in terms of integral pressure over the surface. So at this kind of approach, we're going to apply what you've done in year one to thrust. And we're also going to apply an integral formulation to look at changes in flow properties. which is going to be a big component of influence of friction and heat on pipe flow. So that's it. That's why we study compressible fluid mechanics, and that's an overview of the material we're going to cover. Thank you very much for listening.